Hello everyone, welcome to this last session of this course on PLL. So, I would like to just summarize what all important things have we learned or during this whole course. So, one important the our final goal was to learn how to design a phase lock loop, and what we learned after a lot of analysis, analog charge pump PLL, charge pump phase lock loop. It was discussed in great detail, so that whenever you would like to design a PLL given the resources, you can design the analog charge pump PLL. The block diagram of this analog charge pump PLL, you had phase frequency detector, and the output of the phase frequency detector goes to a charge pump. We have seen multiple many methods how to implement the charge pump, but basic block is only this, that you have current sources, you have switches, and that is the only thing which you need to control. The output of the charge pump goes to a loop filter, a passive loop filter with RC1. Then you had added additional capacitor which is C2. The output of that goes to an oscillator which generates the frequency with respect to the control voltage. The oscillator output is divided with a frequency divider, where the divider operates on the frequency of the signal and not on the amplitude. So, actual signal here is V in, this is V out. In terms of phase and frequency, you have phi in or F in, which is the reference frequency in general, and then you have here you can look at that as phi out or F out. Okay. So, this is like up and down, the current source ICP here, this is a small ICP which I am writing, this is V control. So, this is the basic charge pump PLL which we discussed in this course. We arrived at this architecture after understanding lot of requirements from the PLL. The PLL is considered locked if you have F out equals to n times F in or F ref, and the rate of change of phase error is 0. It should not be increasing all the time. Okay. So, to begin with, this is our main requirement, and we implemented this. PFD measures the phase error between the input and the reference signals. It gives you pulse width modulated output in terms of up and down. The charge pump, which is this block, the charge pump converts this pulse width modulated phase error to pulse width modulated current ICP. ICP is actually integrated by the capacitor C1, okay, and C2 also here is integrated by the capacitors, which give the control voltage you desire for the given output frequency. Okay. So, here we added this resistor here for the stabilizing the loop, otherwise you will have only two integrators in the loop which will be unstable. Okay. And then we looked at in the detailed design of PFD, charge pump, how to have this loop filter and oscillators. We talked about the low swing oscillators, the full swing oscillators, large swing oscillators, and we went ahead with the supply regulated VCO also. We went ahead and designed like this oscillator was not directly controlled in this manner, it was controlled using a voltage regulated design. So, we had a voltage regulated loop which controls the current through the oscillator. Okay, and this is VDD, this is VDD, VCO in our case. So, what happens here then, when you have a supply regulated oscillator, you will have to stabilize this loop also internally, right, and the overall loop should also be stabilized. So, we mostly what we do, we design in such a way that from V control to VDD VCO, you have a bandwidth which is much larger than the PLL bandwidth, 4 to 5 times bandwidth of this regulator loop is quite convenient to design it. Okay. So, we talked about different methods in which we can we can have the supply regulation for the oscillator. We looked at single ended oscillator, pseudo differential oscillators with cross coupled inverters between the oscillators and with feed forward resistors from the power consumption point of view. So, this is the, you can say, a very basic charge pump PLL which you may need in many different applications and which you can design. Now, then before this particular block, this was our main focus of the course to design, but before this we also try to understand how your phase and frequency variables change in large signal analysis also, right. So, there we looked at your pull in frequency, pull in range, hold in range, lock in range for a simple PLL. The simple PLL which we started was just a mixer based phase error detector, which was like this, and then you had a very simple loop filter, or the same, you can have the loop filter which you want, but loop filter and an oscillator. So, our starting point was this. Now, you just think about it. The starting point was this at the block level, not you can say it's just a model. You have a mixer, you have RC filter, and you have an oscillator with designed characteristics. We looked at the frequency acquisition in such kind of PLLs. When as soon as you start the PLL, what will happen, and then from here slowly we build up from mixer we came to the phase error detector, then phase frequency detector. From the loop filter, because of the limited acquisition range, we came to the type 2 PLL, which has this RC, where RC became must to acquire the frequency which we want, right. And then because you had this R there, you had ripples, so you added a capacitor C2, and that is how we came up with this loop filter. Then conversion from the phase error, which here you see that this mixer output was only VPD. The average was done using the loop filter. Now, we need to convert this time, because in place of using sinusoidal mixers, we are now using square wave clocks. So, we need to convert this pulse width modulated signal to our equivalent current or voltage. The current summation was easier. So, we added ICP here. So, this is how we converted, and then we came up with the after this we control the oscillators. So, that is how we come to know about it. Then for the frequency multiplication, we need to have the frequency divider. We looked at a simple divider using D flip flop or TSPC flip flop, where we can easily divide by 2 power n numbers. We also looked that we can get different frequency division by using a cascade of divide by 2 or 3 circuits. After doing all this, we actually went ahead and found the problem with this kind of PLL, that this capactor takes a lot of area. So, if this capactor takes a lot of area, can we replace this capactor using a MOSFET which has a higher density? Well, that led to leakage issues. We could not do that. So, we replace this integration which we are doing using using a digital accumulator because we know that as you go down lower the technology, having a larger voltages is not possible, and process variations for RC are a lot. Implementing a digital accumulation is much easier. We implemented this with a digital accumulator, right. So, then we build up on that, and finally, we had this block where we had a TDC which converts the phase error in its digital equivalent. Then the loop filter became digital, which is Kp, and then you had Ki. This was our digital accumulator. Okay, so we represented this block as an accumulation like this, and these two were then added with Z inverse here. The output of this and this, they go to another accumulator given like this. Okay. Then you had digital value, so you needed to have a DAC, and then DAC controls the oscillator. Oscillator output is fed back in this manner. So, in this case, this is the basic digital PLL, just replacing all the blocks by their digital equivalent, which gives us bits like 1 or 0. So, here we had the reference clock, we have output clock here, right. The output of the TDC is digital bits DTDC, and everything is in terms of bits here till this point, which is the control word for your DAC. When we did this, we found that the quantization noise of the TDC is one of the biggest problem for this digital stuff, and no matter the benefit which you have got with by removing the loop filter capacitor and replacing it by the digital accumulator, TDC quantization noise is just spoiling the party. So, what we did, we said, okay, let us separate this now, digital accumulator part or the integral path and the proportional path, and then we came up with this hybrid PLL, where you take you give the input to PFT, and PFT output is taken by our proportional path DAC, which feeds directly to the VCO without any quantization. The output of the PFT goes to a TDC, and we could implement a 1-bit TDC without any error in the polarity of the frequency error detected. This goes to your accumulator, and then goes to an accumulator, it goes to IDAC, and they both control the oscillator then. Okay. So, this is what we did. Then very briefly, this particular PLL has now become a hybrid PLL. Okay. So, this is reference, this is output, this one is digital PLL, and this is our hybrid PLL, hybrid analog or digital PLL we call it. Right. Then we looked at how we are going to implement proportional path DAC such that there is no quantization. We realized some problems with IDAC, that you need a range and you have a range and resolution trade off. So, we replace the direct control of IDAC with the digital delta sigma, and that is how we implemented it. So, all these techniques which we have learned, we can surely build up on this while designing ICs, PLL ICs for any given application. The basic concepts remain the same. Okay, so I hope this course has given a good amount of basic or fundamentals to start designing PLLs. Okay, the basic concepts have been covered. Then depending on your requirements, you can choose either of these design, or you can explore more to design the PLL for any given application, whether it is wireless, wireline, ADC, power management or anything, wherever PLL you need, these concepts can be used. An important thing is that this dealing with phase or frequency, it is not limited to PLLs. you can explore more that how this concept of phase of frequency can be applied to for analysis or controlling different other kinds of feedback loops. Okay. So, thank you very much and all the best for this course. Thank you.